So thanks for the invitation, and I am the first back after the vacation, the summer vacation, if I understood correctly. So the aim of this talk is to discuss about the mode of breakup of marginal seas and the way they differ, they are different from the Atlantic type margins. So when we speak about continental breakup, what we have in mind is the classical Atlantic type, end members like the. Sorry, I need to change my. I have to my zoom to finish. Anyway, I have the Atlantic type magma pool rifted margins as the Iberian Newfoundland margin, where you have a succession of tilted block leading eventually to exhumed mantle with little magmatism, and after moving to oceanic crust. So this has been called non-volcanic margin, but there is volcanism, so name change, and it's called magma poor margin. This has been well documented by IODP and ODP wells in Iberia and Newfoundland margin. On the other side, you have what we call magma rich or volcanic margin, and in that case, you have rifting still associated with a large emplacement of magmatism, the so-called SDR, seaward deep reflector, that are subaerial lava flows with a depth, high velocity, low crustal body, often interpreted as gabbroic intrusions. So this is two different continental ocean transition associated with two different parameters on per se crustal architecture. So the aim of this talk is to go in other parts and to see what are the mode of breakup of marginal seas, what are their style of rifting, and how can we compare this mode of breakup? Are they similar to Atlantic type, or are they different? In the past, most of these marginal seas have been related to magma poor, to the first one, and I will show you that in some places there is a specific mode, or a mode that is more prone to develop in continental marginal seas, and that differ from the Atlantic domain. Okay, so what is a marginal sea? So this is a big question, but in my talk, I will speak to extensional basins that developed in convergence setting. And these marginal seas are often controlled by or associated with nearby active subduction zone. They are often related to back arc basin, but they are not always back arc basin, and they can also develop in a lower plate setting. And here, to illustrate these marginal seas, the best place on Earth, in my opinion, is the Southeast Asia, where you can see through the Cenozoic the development of several back arc basins associated with subduction zone. You have the Proto-South China Sea that was eventually subducted, or the one that we will more discuss today, the so-called South China Sea. So these marginal seas, they have many specificity, in my opinion, and one of those that is very important is the fact that in many places you have a continuum of deformation from an orogenic phase, followed by a post-orogenic collapse, and eventually the rifting. All of that without any breaks, without a lithospheric re-equilibrium. It means that you have a strong inheritance in terms of structure, but also in terms of thermal states. And this, as I will show you, is likely a key feature of the mode of breakup of marginal seas. Okay, so I will now focus on the case study of this talk, which is the South China Sea. It is located offshore south of China, Philippines to the east, and Vietnam to the west. And this marginal seas is a Cenozoic marginal basin characterized by very wide rifted margin, as you can see on the figure below, where the margin can be more than 850 kilometers, with a kind of pinch and swell or boudinage structure, where you have basement high percent basin, then basement high again, and you have a succession of boudinage at crustal scale. This margin developed over a former Mesozoic active continental margin, and it is associated therefore with a strong pre-rift inheritance. If I show you the rifting style of this South China Sea, thanks to an amazing, in my opinion, seismic section provided by PGS, you see that many of these rift basins are associated with what we call today low-angle normal faulting. So on this seismic section, which is in depth 1-1, as a geological section should be, you can see very high angle normal fault, 20 degrees, 15 degrees that you can fall. And this style of low angle normal fault, here you have the interpretation, is very common in the South China Sea, in the northern margin, like the Liuan and Beiyun, or in the dangerous ground. And many publications propose that this style with low angle normal faulting active during the rifting is in fact resulting from the reactivation of former thrust fault from the Mesozoic orogenic phase. Now, if we go to the core of the talk and we have a closer look on the northern margin of the South China Sea, here, thanks to no very high quality seismic data, we can image the continent-ocean transition zone. And sorry, I will just change because I just need to remove the zoom thing that is on the unit. Sorry. Perfect. So if you look this, I do not have any more my pointer laser. Yeah. Anyway, if you look this, you have three seismic sections that illustrate from left the continent and to right the oceanic crust. And I will show you that this seismic section should preserve the continent-ocean transition and the same crustal architecture. So if I choose to look first on this one and after on the other, this one here, if I show you a zoom, we see quite well here a deep reflector dipping towards the ocean. Here you can see a deep reflection close to 10 seconds that is related to the MO and associated here with two ridge A and ridge B. Why I focus on this seismic section? Because they have been drilled in 2017 by two IODP expeditions, 367 and 368. Therefore, we have drilling calibration. So if I show you this seismic section and I show you my interpretations, you have here a very nice low angle normal faulting that you can see here associated with a transition with here an oceanic crust, 2 seconds, as you may expect from oceanic crust. Now, if we have closer information from what is in between, thanks to the drill hole, what we can see? What we can see here in a projected well, here we have evidence of conglomerates derived from the continent. So meaning that here we have late or post-rift sediment with no mafic input, only felsic input, therefore deriving from the continent. From the same ridge A, we drilled there basalts. They are morb type, highly weathered, highly hydrothermalized, with evidences on top of Saint-Rift sediments. And then if I move oceanward to what we call ridge B, here we find again basalts, morb type, but they're fresh without any weathering. So our interpretation at that time, and it's still my interpretation, is that through this slide and through this seismic section, we record the sharp, in space and time, thinning of the continental lithosphere accommodated by a low angle detachment faulting in red, cross-cut by late Saint-Rift volcanism that will trigger or will pass quickly in space and time to a fully igneous oceanic crust. So a very sharp transition between continental basement and oceanic crust, with here no evidences of exhumed mantle as magma poor margin, but also no evidences of SDRs or huge magmatic input as you may expect with magma rich margin. Now, if I zoom out and I do that with the other seismic section that I show you, similar seismic observation and interpretation can be proposed with success, with always this low angle detachment fault associated with magmatism, late Saint-Rift magmatism that sometimes overprint the extensional structure that you can see in this three seismic section here further to the northeast, where you see nicely the fault, small faulting, some blocks, and a sharp transition with the oceanic crust or the oceanic lithosphere. So very along strike variability, but still we can find the same style. Now, is it only the South China Sea that show this style of breakup, meaning low angle normal faulting associated with Saint-Rift volcanism and then a sharp transition in space and time with oceanic lithosphere? No, I think here I will show you two other examples from previous work not done by me on the Woodlark Basin and the Coral Sea. I will first start with the Woodlark Basin and then move to the Coral Sea. So here I rely a lot on the work of Goodlife and Brian Taylor.
Here we are, the Woodlark Basin is still a propagating rift, so it's a very interesting place because we are at the moment creating new oceanic lithosphere and continental breakup. And when you look at the tip of the Woodlark propagator, where we have not yet reached continental breakup, what we can see here this two faults that delimit the North Moresby Graben. And this fault, the Moresby fault, has been based on earthquake, on geophysical studies, shown that it is a low-angle normal fault active at 30 degrees. So again, activity of a low-angle normal faulting. And it delimits a graben, the North Moresby Graben, where the crust is seen more less than 15 kilometers over 20 kilometers. Now, if I just move further east, then we are at the first breakup, or the first segment, or the segment that breaks at the moment. And here we can see the similar geometries, a low-angle normal faulting, and evidences of dikes and sun-rift magmatism that lead with continental breakup and initiation of seafloor spreading. So here you have the interpretation of Goodlife and Taylor, and you see low-angle normal fault cut by dikes and magmatism that will lead to continental breakup. So in a way, exactly, or more or less exactly the same style of breakup than the South China Sea.
You're just past 11 minutes, okay?
Sorry?
You're just past 11 minutes.
Yeah, so I'm time. So then if we go now to the Coral Sea, so there is less information on the Coral Sea. There is less data available, but we can see again here the same. So if I show you the first section, which is a bit oblique, here again, same story, low-angle detachment faulting and a late sun-rift volcano passing to the first oceanic crust. Same for this one that has been published by Sapanetta 2021, where we see a low-angle detachment fault, some rider blocks, and here we see evidences of seals, magmatic seals, and strong reflectivity in the crust that has been interpreted as underplated body, likely during the rifting, and then the oceanic lithosphere. So again, the same, I would say, interaction between extensional deformation, late sun-rift magmatism, sharp transition in space and time between continental basement and oceanic crust. So if I sum up, what we can see, in my opinion, that we have here shown the same mode of continental breakup of the South China Sea, through the South China Sea, the Coral Sea, and the Woodlark Basin. And always associated with longer normal faults and MORP type late sun-rift magmatism. So the question is, what are the driver for such mode of deformation? And for me, there is several key driver. And one of the keys is the fast extension rate, because we are close to subduction rate. We are dealing with microplate, and this will trigger high extensive rate that are documented in the Woodlark Basin. We are more between 20 millimeter or 40 millimeter a year. So it means a fast extension rate with little conductive cooling. So meaning that when you see in the lithosphere, when you reach a beta of 4 or 3, you initiate the MORB machine, and then you have no conductive cooling, and you will go quickly to continental breakup. And then you are also associated with a highly thermal state and inheritance that will promote or enhance the activity of low-angle detachment fault. So now if we look the comparison with the Atlantic domain, you can see that we are in a kind of intermediate state. So intermediate is a word that has been used by several authors, and it is still discussed. The point what I would like to stress here, that we in a way exemplify the diversity of the mode of continental breakup, and it's not only black and white, and you all have different color of gray, dark gray, light gray, and so on. So in Iberia, we have this wide COT exumantal, likely with very slow extension rate, therefore very little magmatism, because you have an efficient conductive cooling associated with tectonic exhumation of the subcontinental mantle, leading eventually to oceanic breakup. In the other way, in the mid-Norwegian margin, for example, you have a plume, you have the North Atlantic magmatic province, and you are associated with SDRs, with gabbros, and you have
here a huge magmatic budget. And in between, or in intermediate, as you want, you have fast extension rate associated with a normal decompressional melting, as you will expect for rifted margin in classical model. So what are, for me, the key parameters? This is always a very tricky and complicated question, and this is a non-exhaustive parameter, but I think for me, some key of this parameter is the extension rate. Magma poor, in my opinion, are associated with low extension rate of the breakup of big plates. So you are going slowly, so you are not producing a lot of magma to conductive cooling. You have not thermal anomalies associated with that. While on the marginal seas, here you have fast extension rate, you have a strong inheritance, strong thermal state at the beginning of the rifting. Therefore, you will promote fast breakup during the final stage of rifting. While on the other way, the magma rich is controlled by thermal anomaly and, of course, inheritance. So I will leave you with my last slide. That is just a comparison of the three main modes of deformation of the magma poor, the Iberian Newfoundland margin, the South China Sea, and the South Atlantic margin. And I leave you with this conclusion. And I hope that I am in time.
Thanks, Geoffroy. Yes, that was perfect. If anyone has any questions, they can put it in the chat or raise their hands. In the interim, their virtual hands. In the interim, I know that Derek has a question.
Yes, Geoffroy, thanks. It's a really interesting presentation. I have a question about the timing, or how well constrained the timing of these late synref magmatism is. What's it based on? Because it kind of looked like some of the seismic sections, it kind of looks like the sediments just onlap these basin high areas that you've interpreted as a, I don't know, synref volcano or intrusion zone. So I was just wondering how, the timing has been constrained.
Yeah, good question. So in the South China Sea, I would say it's very well constrained because we have drilling constraint, because in the well 1502, we drilled pillow basalts. This is those ones that are highly weathered. And directly on top, we have sediment where we found benthic fauna that are latest Eocene. And the breakup, because we have magnetic anomaly, is 30-ish, 31, 30-ish. So it means that here we have a very good dating, meaning that this volcanism needs to be placed at the latest Eocene, just before the early Oligocene. So we have an interval of 1 or let's say 3 to 4 million years. So we know that this breakup initiates at the very, very late rifting stage. So here we have very drilling control. On the other example, we are less constrained, but we can often see that we are rely on seismic interpretation, and as this magmatism cross-cut the North Moresby or the Moresby fault, and in the Coral Sea, the Saint-Rift sediment or the post-rift sediment, unlaps this volcano. So meaning that they have somehow to be placed at the latest post-rift, early post-rift, late Saint-Rift. But on the South China Sea, we have very good drilling control to say that this magmatism placed at the late Saint-Rift. Doesn't mean that you cannot have magmatism before, because some people describe Saint-Rift magmatism more continentward, but at least here in the COT, you have very late Saint-Rift magmatism.
Okay, thanks. That makes sense, because the sediments are post-rift then. I was thinking those were synrifts. So that's why that explains things. Thanks.
And Geoffroy, I think Fola's got a very quick question, he promises.
Yes, thank you very much for your talk. Quick question. Do you have any insight into the structure of the lithospheric mantle across the CO2 here? Because, I understand all your interpretation is they're just based on the crust, but there does not seem to be any comment on the lithospheric mantle part.
Correct. Good question. So, of course, for the South China Sea and, we'll use this globe. For the South China Sea and the Coral Sea, we have thermal reequilibration because the breakup occurred a long time ago. But from our interpretation, yes, during the breakup time, the asthenosphere needs to be shallow, with close to the, let's take this. We should have a very shallow asthenosphere and rise of the asthenosphere. Now, the question that I don't know if I will answer to your question, but what a key point for me is also mantle heterogeneities, because if you look the source China Sea, and sorry, I will go back. It's not good when you are changing slide too much. Sorry, I will come that. But we have a lot of for me, the key role is mantle heterogeneities. Why? Because if you look the source China Sea, you have a lot of hyperextended basin. Here, the crust is highly thin. Here, the crust is highly thin. Here, the crust is highly thin. And the question that I ask myself, why on Earth breakup occur here and not here or not here? Because on every cases, the crust is less than 10 kilometers thick. You would expect high beta, shallow asthenosphere. But for one of the reasons, the main magmatic budget, the main magmatic input on place here. And my interpretation, which is only my interpretation, is I expect maybe that you have mantle heterogeneities and more easy partial melting of the asthenosphere that will focus breakup to this position. But this for me remain a open question that's puzzle me.